to like 80 hours.
Everything is
before you
ready to
guys
go.
start deploying Vader.
Okay, so we are gonna get ready for our exam 2. That is gonna be 1 week from today. Okay, not today. 1 week from today. All right. So the exam is gonna have a few different types of questions. Those questions are already on the shared drive. So let me show you where to find the past exams that is relevant of studying for this particular exam. So let's go to courses, go to this class. you can find it in the shared folder. So when you go to the modules and locate the share folder here, I'll just open a new tab. In fact, I'll close all of my other ones just so that they don't interfere with what we are doing here. So when you open the share folder, you will see the usual stuff, the processor, but there's also the exam 2 down here and also the final exam here. Some of the questions will be coming from the final exam because we covered enough material already compared to last semester that some of the questions will be similar to the questions that I asked in the final exam last semester. But we'll also have something that's coming from exam 2. Exactly how much is coming from each one, I have not determined yet, and that probably won't be determined until next Monday. So if you want to ask me that, I would probably give you an answer that may not be what you're looking for. Okay, so let's take a quick look at Spring 17 Exam 2. Okay, you have access to this one as well. All right, so it's open book, open notes, just like with Exam 1. Okay, so I strongly suggest you to start preparing your material for the exam. Okay, anything that's either handwritten or printed prior to the test, you can bring it with you. You can work in groups if you want to. Okay, if you find a study buddy and you go like, okay, let's work on this together. You can share stuff as long as it is not being shared during the exam. Okay, so if you want to bring in exactly the same handwritten or printed notes, to the exam, hey, it's all cool. Okay, no electronics during the test. Just open book, open notes. All right. So this is the kind of question that I asked last year, which once you kind of take a look, you know that, okay, that's not going to be asked this year. Because last year, I did not have the increment or the decrement instructions implemented at the time. And that's why, I can ask questions like this, okay? So we want to implement, increment and decrement instruction. And at the time, the processor architecture did not have the necessary pathways to do it. So the first question is basically asking, tell me why this is not possible. This is how come we cannot do it at this point, and what needs to be done in terms of components, connectivity, in order to support these two instructions. Okay, your answer should include a statement of what needs to be done in terms of component port connectivity and how the current architecture is not supporting it. Okay, which is not applicable to this class anymore because our current computer architecture or processor architecture clearly supports it because we have the increment and the decrement instruction already. So instead of asking this question, let me change the question a little bit so that it becomes relevant to this class. Okay. So we'll switch to this thing here. Okay. And we'll start a new page. So in our class, okay, it is more relevant if I want to okay, so first of all, okay, use the wrong tool. There you go. Okay, so I hope we all remember what is the LDI instruction. It basically initializes a register, which I will call X here. X can be register A, B, C, or D with an immediate variable or immediate constant. So the I is either a label or a number that you can spell out in decimal. Okay, we have used this instruction many times already. So when you look at the underlying operation, it is basically oh, okay, I probably want to turn on a palm rejection. Go to settings, go to input. We want to turn off one finger scrolling, turn off two finger scrolling, so we're not maybe 2 finger scrolling, because my palm, should not look like 2 fingers. Okay, after zooming, I still want that. Okay. So let's see how well that works. Okay. Okay. So 2 finger scrolling still works, but with my palm, it doesn't. It has pretty good rejection, not 100%. Okay, so in this case, it really is the register X, being assigned the value of whatever the program counter is pointing to. Okay, and then after this, we have increment, post increment of the program counter. That's what it is, equivalent to. Is that okay so far or not? Okay, so here's the first question. Okay, how do you study for this class? What material is available for you to study so they can prepare for the test?
The processor?
Everything, right? Everything in the share folder. You mean really all of that stuff? Yes, all of that stuff. Okay, so the bottom line is I want you guys to show me that you understand how the processor works, how the microcode works, how the components inside the processor connect to each other, and how to control the multiplexers and the demultiplexers and the enable and stuff like that in order to get something done. Okay, that's what I'm testing, at least for the first part. The second part has to do with actual programming. I give you the C code, you convert it into assembly code, or I can give you the assembly code, you convert it back to the C code, or I can give you the assembly code and the C code, and you tell me what is wrong with the implementation in assembly. So those are the things that I'm going to test you on. Okay. So the question now is, with just this instruction, the LDI instruction, which we have used a lot in all of our programs, okay? Because every time you want a specific value in a register, you need this instruction. But how does it work? Okay, in terms of, okay, which parts of the processor do we exercise, okay, and how do we, actually get something into the register? So we'll get back to this later, okay? But tag once. Okay, tag wants another instruction. I want this instruction, which seems to be pretty handy. Add immediate, xi, and the effect of this one is I want x, register x, to be x plus whatever the program count is pointing to. I'm going to put in extra parentheses just to emphasize that we are dereferencing the program counter. And then after this, I also want to increment the program counter because otherwise I'll be executing the byte that is specifying the constant, which is not what I want to do. Okay, so when you compare these two instructions, they are pretty close. The question is, how do I implement, can I implement the add-I instruction using the current architecture without adding additional components or changing the ROM in any way? That's the question. So if that is the question, how are you going to answer that question? What is the first thing you reach out to, and then you start investigating?
The opcode table?
Sorry, go ahead.
The opcode table?
The opcode table. Okay, so what is the opcode table going to do in this case? So let's go to the opcode table. Okay, I'm going to go back to the share folder. There's a opcode table spreadsheet, and we'll open it up. And by the way, all of this stuff here, you can print it out and bring it with you. Okay, anything that is either handwritten or printed prior to the test, and that includes all of my material. Okay, everything in the share folder. So when you look at the opcode table, we can locate LDI, which is this one, and I can zoom in just a little bit so that we can actually see the entire row a little bit better. There we go. Okay, so it's really saying the same thing as what I have on the other sheet. It's just represented slightly differently. But that's not going to help you to determine whether the current architecture, the current processor, can implement the instruction that I'm proposing. Is that okay? So what else do you need to look at? What else are you going to bring to the test to help you and go like, okay, so I need to look at this, study that in order to answer the question. What else? Yep.
Maybe the toy processors with the manual?
Exactly. Well, not so much the manual, okay? The manual is not really the root of the information.
The processor itself.
The processor itself, yep. So what I'm gonna do is I'm gonna look at, so I'm gonna use 1998. I'm just gonna start up the Logisim. Okay, this is one of the most important thing you should bring to the test. Okay, it's the processor architecture itself. Okay,
Print it out?
you can print it out. Yeah, absolutely. So you can go to File, and then you say Print, and you can print main all by itself. You can rotate to fit, print to view, click OK. And of course, I don't have any printers attached to this particular computer, but you can do that. You can do it. You can also do something else. I mean, if you want to do some editing on your own and do some funky stuff with it, that's fine too. Export it as an image. So when you export as an image, it will give you the options of saving as PNG, GIF, or GIF, okay, JPEG or JPEG or GIF. You also have a scaling factor, which means if you zoom in, you get to it's more detailed, but the file will be slightly larger. This is not a picture. It's not a photograph of any kind. It doesn't have a lot of details. So it doesn't really matter how you zoom. It's not going to be a huge file. It will still be reasonable. The printer view is a little bit different from the non-printer view. The printer view will not have the values represented here, but when you have the printer view, it will display the values. So experiment a little bit and find out what works best for you. Okay, so I'm just going to scale to 2000. Click OK. Okay, save the file to my temp folder, because the temp folder gets nuked every single time I reboot a computer. This is not something I want to keep. So you can just say processor.png, okay, export, and I think it's all done. Okay, so the next thing I can do, since I have to explain all this stuff here, so it would be helpful for me to start up GIMP or some other software to convert it, okay, so that I can use the image on my tablet. You can use the GIMP if you want to. It's open source, available to all major operating systems. You can use something else if you want to. Doesn't really matter. So I just need to go to the temp folder. Okay, with a slash. Okay, locate my processor PNG. Okay, so it looks kind of. Okay, let's see. I press 1 and that will give me like 1-to-1. That's pretty detailed. Okay, if you print this out, okay, and assuming you have a pretty high resolution printer, I think it's going to be sufficient. Okay, if you have eyesight issues, you can always print it in a tile type of format, and then you stitch the whole thing back together using Scotch tape. Okay, that works. So what I'm going to do here is I will export this or print it as a PDF. So let's see, export as, and I think I can export it as PDF. You would hope so. PDF, is it on the list? Nope, no PDF. That's okay. If there's no PDF, then we'll print it to a file, and the PDF in this case, and we'll specify the temp folder. Make sure it is the actual temp folder. Okay, and I'll call this processor.pdf. Print. So it will now create a file over there. To use it on the tablet, I have to go through one more step, because I have to go to the shared folder, or some kind of shared folder. It doesn't have to be the specific one that we are using, but since we're here already, might as well use it. So I'll go to the processor folder here, and I'm going to upload the PDF so that you guys can use it too. I'm helping you guys with your material, which also means I don't want to hear anyone saying, but I don't have the processor printed out with me during the test. Okay. All right. So now that we have this, done over here, I'm gonna. Okay, you guys can watch me do this. Okay. So this is back on the tablet. And on the tablet, there's a way to import PDF as a new notebook, which is this option here. And it can only import from a Google Drive. So I'm going to select the right drive. We go to the 310 shared processor, and it is the process.pdf, which is just created, and select that. It's importing that, and it should import as a single page with that kind of resolution, which is, I think it's good enough. And create and open. And now we have the entire processor as as a PDF in my tablet. So you can print it out. You cannot have your tablet during the exam, okay, unless it's a stone tablet. If you want to use a Dremel and just say I can etch the the design on a stone tablet, you can bring that with you as long as it doesn't break the table. But I know they're high-tech material these days. They have stone properties, but they weigh as light as plastic. Okay, so is that okay? This is important. Okay, make sure that you have this with you along with the ALU and also the register bank. The register bank I'm not too worried about because it's really kind of simple. The ALU you might want to print too because the ALU contains a whole bunch of information as well. All right, so when you're here, then remember the instruction that we're trying to implement. Okay, so we'll, it's not letting me zoom. Why is it not letting me zoom in?
I think you turned it off.
Huh?
I think you turned it off.
I turned off.
Maybe.
Okay, gesture, this is for, see, allow two fingers zoom when zoom is active. Okay, so why is it not active? Okay, guess in display.
There's something about double tapping too.
Okay, let's see. Nope, I think I got zoom disabled.
Like a zoom tool right there. But there's
Right, zoom, there you go. There we go, now we can zoom. Cool. Okay, so two finger scroll and then two fingers zoom. Perfect, okay. I can play with this all day long until you guys all pass out. I used to have a teacher, and okay, I know we're wasting time here, but I used to have a teacher. He was using one of those overhead projectors from the good old days, and he has a habit of using a pen, and when he's thinking, he would look up into the ceiling, and he would just kind of mumble, and his hand would be doing a circular motion on top of the projector. So the entire class would be seeing the magnified version of the pen, swirling. So of the 60 people in that class, about 30 will show up in class, and of the 30 who show up in class, about 12 will stay awake. The teacher is fine. I mean, he's a great guy, but it's just staying awake in this class is kind of difficult for me. All right, so now that we have this picture, how do we figure out, can we implement that instruction? How do we do that? We want to be able to add an immediate constant, okay, which is a part of the instruction, to a register. That's what we want to do. I'm asking the question, if you do not modify the existing architecture, can we do it? If not, what is missing here? That's the question. So what do you think? Where do you start with this whole thing? Register bank and
RAM.
Okay, RAM is important. Okay, so we know that RAM is important. Okay, so if I switch back to, oh, this is going to be a little bit difficult because I got it in the other one, but I can always annotate here. Okay, so I can annotate here and use a different color so it's it shows up a little bit better, and probably want to use fine. Okay, so the instruction that we want to implement is LD, oh not LD, but
ADD.
yeah, it's ADDI, add immediate X with a particular constant. But the way it's going to be implemented is going to be register A X equals to X, oops, alright, sorry about that.
X plus
My palm touched the edge of the tablet. So it becomes x plus whatever the program counter is pointing to.
Plus plus.
And then we can separate these steps. Okay, so we can have PC++ as the next step. So we'll worry about the first one first, okay? Because the first one is already enough to say that, oh, I guess we cannot do it, okay? So whenever you see the star PC, it means we're accessing memory, we're accessing RAM, which also means, one side of the operation, but who is doing the adding? There's only one component that can do the adding, which is the ALU. So we need to get the register into the ALU. That is not a problem, okay? We got paths to do that. So the way you analyze the design here is you basically look at the inputs to the ALU. So you basically say, okay, what can possibly feed into in1? So you can see that in1 goes to the multiplexer. Okay, can you guys see the red?
No.
Just faintly? No? Okay. I can make it thicker, medium. There we go. So you can see this line here.
Oh.
Is that better? Okay. So in1, can be fed or has to be fed by this demultiplexer. And this demultiplexer has one input. Okay, remember a demultiplexer has one input and multiple output. A multiplexer has multiple inputs and only one output. So, but the demultiplexer has a single input, which is coming from the register bank, which is fine. Okay, so this is what is going to be supplying X, the register. Okay, that's not a problem. We want the result to be stored back into a register. We don't have a problem with that either, because the output of the ALU, which is this line here, okay, if you follow it, it goes into a multiplexer, and the multiplexer, depending on how you set up the multiplexer, it does go back in to the input of the register bank, which means we can use the output of the ALU to update one of the registers. Okay, so that's cool. We can get that part done. So the red part, okay, is indicating we can get this part done. Okay, this part is okay, we got it. This part, we got it too. Okay, the addition part by itself is okay. We have the ability to add inside the ALU. What we cannot do, okay, is a path of the coming from the RAM, from the data port of RAM into the second input of the ALU. In other words, what we are missing, which I'm going to use green. Okay, so what we're missing is here. Okay, we have this input here. Okay, and I somehow need that to connect to the output of RAM, which is here. So if I follow this line, okay, and this line goes in several directions, but it doesn't matter how you track it. It does not go into the in of the ALU. That's just no connectivity. Okay, so when you look at this green line, you can track down the entire thing. Okay, it goes all the way here. Okay. You can use it to update one of the registers, but that's not what we are trying to do. You can also use it to update the program counter itself, okay? But that's not what we're doing. You can also use it to update the instruction register, but once again, that's not what we're doing. So you can see the green lines, the two segments of the green lines are not connecting. There's no way to connect it. There are no multiplexers or demultiplexers to switch and say, now you guys are connected. So that's why the instruction cannot be implemented. It doesn't matter how you code the microcode, there's just no way to do it. So is that okay so far? Yep.
The add I, does it add, does it have the same syntax like register x comma 5? Give it a number to add into the register.
You are giving it a memory. You're giving it a constant, correct? So it has the same syntax as LDI. Add I would have the same syntax as LDI, but instead of initializing the register, you're basically adding the constant to whatever the register already has. That's what you're asking. Okay. All right. So that would be the answer of this particular question is it is not possible because we cannot establish a path between the data port of RAM and into of the ALU. Okay. You cannot. You don't have to tell me why there's no path, because if there's no path, there's no path. They simply do not connect. But it is important to identify which two parts or which two ports cannot be connected, and that's the reason why we cannot implement the instruction.
So
Yep.
from the instruction, we wanted to all to be immediately added into it. The ALU not go all the way around.
We do not want to waste another register for that addition. Okay, so the only one register that is modified is X. We don't want another register to store the constant to be added. So I want that to be implemented directly. I don't want any other register to be clobbered, which is the whole point. If I can clobber another register, I can just do an LDI instruction with another register and then add the two registers. Is that okay? All right, cool.
Can we also
yeah,
say,
go ahead.
Can we also say, like in our setup, if you want to perform a calculation, it has to be only registers, because that's the only way we can send inputs into the ALU.
But that would not be the answer that I'm looking for, because I need to know that you understand that in order to implement this particular instruction, you need a path that goes from the data port of RAM into or in one of the ALU, and there's no path connecting. There's no possible path in the current architecture. Okay. So is that okay so far? Okay. So if you think about it, okay, this is something for you guys to think about. Is okay. So how do we fix this problem? Okay, if TAC is obsessed with implementing something like this, how would you modify the architecture in order to support this particular instruction?
Could you could you add the RAM output to the multiplexer? Something
Okay.
like that?
You will need to add some components. Okay, so one thing you can do, okay, is to look at. Okay, let me find out which one we're talking about. One thing you can do is to change this multiplexer so that it uses like 4 inputs instead of 2 inputs, and one of the pathways will be coming from RAM. Okay, so that's one possible solution. Okay, so let me highlight what I'm talking about here. So using blue, okay, which is a proposed solution, is to change this particular mux so that you have. Can you guys see the blue? Okay, so you can basically use this mux and have this particular mux connected to the green line like that. Well, that is simple. That's easy to do. Okay, but by adding one more input into this mux, it needs one more control line, because you need 2 bits to switch. Okay, which one of the 4 inputs do we want to use to feed into of the ALU? So now the second bit of the selection, in addition to FC, needs to go from somewhere. Okay, so now the question is, how can you add one more bit to the select input of this particular of the blue mux? Okay, the mux that is currently highlighted in blue, so that you can control that, but without any side effect to existing instructions. Okay, which is part of another question. So if you go back to all the questions, the second one is related to this one. So the second one, oh no, I take it back. The third one. So the third question is, they're all related. So the third question gives you the fix already. Back in those days, this was not there. This was not there before, and I just added that. In other words, I can ask you a question and say, okay, this is the change to the circuitry. Okay, but what are you going to use as an expression to control that multiplexer. But I want to make sure if you read the instruction, okay, the instruction says right here, your job is to figure out how to specify the equation for the extra control pin, so that I don't want to add any extra bits to the width of the ROM, because that is a lot of work. Every time I change the width of the ROM, everything slides, and then I have to redo everything. So I don't want to do that. The second one is I want to maintain the operation of all existing opcodes without changing their microcode. So the way I implement all the existing opcodes, there's the usual add, the LDI instruction, the jump instruction, everything. I don't want to change the microcode for all of those existing instructions. Okay? And the third one is exactly what we are trying to do. So in our case, it is not to implement the increment or decrement, it is the add immediate instruction. So your answer, in this case, should state the expression that connects to the select input pin, which in our case, in this class, is going to be the extra pin, the additional pin to the multiplexer, and explain why your expression will work in order to maintain microcode of all existing opcodes, and from the perspective of current opcodes, how is this change not going to affect those opcodes? Okay? So what do you think you're going to do with this? How do you approach this problem? Yep.
Can you check if the load flag is lit for the RAM?
Yep. So you can combine the load flag with, do you have to combine it with anything else?
The enable flag?
Because we got 2 bits, right? So okay, let me switch back to the document camera. So you're getting there. You're definitely getting there. So we just have to be more specific. So we're changing this mux. We're changing the blue mux here to have 4 inputs. We're keeping FC the way it is. Okay. So we're keeping FC the way it is, but we have to add 1 extra pin, okay, to the select input. Okay. So we have 1 extra pin. It's kind of hard for me to specify here. So I will try my best to do it. Okay, my palm hit the one of the buttons. I think I hit the top. So I have to be careful with that. Okay, so the extra control pin, I'm gonna lead it here, all the way here. Okay, so the suggestion is to use RAM load, which is a very reasonable approach. So we say, okay, RAM. Okay. Can't write. LD. Okay, and that's not a bad approach. Okay, that is pretty good, because if RAM load is a 0, that means we're not reading from RAM, right? So then we are, it's not for this instruction. If RAM load is a 1, we are in fact reading from RAM, and that's an indicator that, hey, it might be a good clue to connect this mux to the data bus. So in fact, that is a very reasonable solution. But how is it not affecting the current instructions? Because for all the current instructions, everything that makes use of the ALU do not use RAM. And all of those instructions has a 0 specified for RAM load. Not only RAM select, but also RAM load. Now, if you want to be safe and make sure that, okay, we absolutely want to make sure that no current instruction can be impacted by this change, I would do something a little bit differently. Let me answer that question first.
So, because FC is connected to the same pin.
FC would still be the same. Yep.
Would it change like the values that they point to, like which paths should be allowed?
We'll figure out how to rewire the mux if we need to, because the blue wire, the new blue wire going into the mux can be attached here, can be attached here, can be attached here, can be attached here. In other words, we have let's see, we have ways to arrange where the new blue line is going to be connected. In other words, we can figure out how to do that part. But at this point, what I do want to point out is the safer way to do this is not to hook this up to RAM load directly, but to hook it up to a gate, to an AND gate. So here's an AND gate. So on one side of the AND gate is RAM load. RAM load, and the other side of this gate is RAM select. So this is safe because this means all the instructions, current instructions that are using the ALU, none of those utilizes RAM. And as a result, RAM select is guaranteed to be a 0, and as a result, the mux, or one of the bits of the mux is guaranteed to be a 0, and therefore, depending on how you connect the new blue wire, this change will not impact existing opcodes. On the other hand, if you specify and say, okay, this instruction needs to go to that RAM location in order to grab the byte to add to whatever the register is, then RAM select has to be a 1, because otherwise the RAM is not responding. And RAM load has to be a 1 too, because otherwise you would not be specifying a read operation. When those two are 1s, then the output of the new AND gate is going to be a 1, and that is going to change how the mux is going to select its input, and you just have to arrange the new blue wire so that it does not interfere with the existing instructions. Is that okay? And then you have to specify the microcode for the new instruction. Yep.
But if you just hook it up like that, won't it like share the same wire as FC?
Yeah.
Yes, because there's no room for me to draw a splitter. So we're assuming there's a splitter here that splits one wire to FC and another wire goes to the new thing.
Okay.
Yep. So yeah. So we have an implicit splitter, right at that junction. I just don't have the room to draw that. So is that okay? But it seems like this means we have to kind of look at all the existing instructions, look at the microcode of all the current instructions, to make sure that we don't have anything right now that can both make use of the ALU and access RAM at the same time.
No, it's not possible.
Why is it not possible?
Because we already did the thing to check for anything. Like, RAM can't hook in yet.
Okay, but we have to make sure. How do you make sure? Okay, so when you look at this diagram, okay, this diagram doesn't actually show you that, okay, but it does show you the component that you want to study. This guy here is what you need to find out, because all the existing microcode slices are stored in this ROM. And do we have access to the content of that ROM?
Yeah.
Absolutely. Can you print it out? Yes. Can you interpret those numbers? Yes. Can you do it quickly in exam 2? Probably not. Okay, so let me describe what we're trying to do here. Okay, so what we're trying to do, if I switch back to the, okay, I can close this now. So quit this and switch back to Logic Sim. Okay, so what we're doing here is to say, okay, we need to look at, okay, we can go to edit content. So we're basically looking at this and go like, we need to make sure that all these slices, okay, all of these are not interfered, or they're not changed by the change to the processor architecture to support that new instruction. Okay, so when you look at something like this, it has everything that you need to know to answer the question, but it is not quick. Okay, how come it's not quick? Let me show you what I need to do if I'm just given this table and also the schematic of the processor. And we can do this. Okay, I can scroll this all the way to the top and then show my document camera, which is here. Okay, excellent. There we go. Okay, so I'm just kind of not superimposing, but so I can see the number, then I can do the analysis here. Okay. So the analysis has many steps. Okay, it's not like it's not possible, it is just a lot of steps. So the first thing you need to do is you say, okay, we're given the hexadecimal number, which is 1880006. Those are hexadecimal digits, which means each digit corresponds to 4 individual bits. So when you write out this entire thing, it is a 0001, which is that 1, 1000, 1000, 0000, 0000, 0000, 0000, and then 0, 1, 1, 0. Cool. Okay, we can do this. Now what do? Now you say, oh, this is bit 0. Okay, so I cannot point on the other side, unfortunately. This is bit 0, which corresponds to this bit here. This is bit 1, which corresponds to this bit. This is bit 2, which corresponds to this bit. Bit 3 goes here. This is bit 4, which goes here, and so on. Oh, I take it back. Microcode data is by itself bits 3 to 23. So that's bit 3 to bit 23, which is somewhere around here. And then you have to look at this and see how that splits up into this entire bunch of stuff. So it will take you a little bit of time, let's just say, to interpret from the actual raw ROM content. Okay? That may not be what you want to do during the exam. Okay? You can do this once just to say that, yes, I know how to do it. Okay? So what do? You need to understand, you need to know the microcode of all the existing instructions, at least in terms of family. You don't, because there are some families that have like 16 variants. You don't need to know all 16 variants because they all look about the same. So what do you do when you want to study? Okay, I need to know what is the microcode for this particular instruction, like a JMP instruction. Where do you look?
Opcode table or
The opcode table doesn't tell you that. Okay, there's a zip file in the share folder. So when you go to the share folder, there's a zip file right here. It's called opcodes.zip. And we talked about that a few times, okay? So let's take a look again today because this may be helpful for you, okay? So we'll go to a terminal and then we'll just take a look at that folder. Okay, so I'm gonna do a make clean. Okay, there we go. And we now have these things. So if you just take a look at one of these, okay, I would do this. A -O means displaying two files side by side. One is jmp.c, the other one is microcode.c. The U is kind of an approximation of mu, as a Greek letter, which is micro. So it's microcode. Okay. So with JMP, okay, it looks like this. Okay, we have a variable that is initialized. It's a two-dimensional array. It's called slices. The first slice is like this. The second slice is like that. These are specifying values of each individual bit field. Okay, so the correspondence is this bit here, or this number, specifies microcode pointer reset. This bit here specifies microcode pointer select. This bit here specifies PC enable, and then this bit here, or this not single bit, but these 3 bits specifies PC mux, and so on. When you look at the microcode table itself, this is the width of a particular bit field. So we have 1 bit, 1 bit, 1 bit, 3 bits, 1 bit, 3 bits, 1 bit, 1 bit, 1 bit, 2 bits, 2 bits, 2 bits, and so on. So the first number identifies the width of a bit field. The second number represents where is the least significant bit of that bit field. And these are all corresponding to the bits that you store in ROM, the microcode ROM. In other words, it's already spelled out. Okay, it's already spelled out like this, and some of these have XX field. Okay, like this one XX field. It is not 1, it's not 0. What does that mean? So let's count and find out what this is. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 11th. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we are talking about this particular signal here, and also in the processor architecture, these will correspond to the names of the tunnels. They are the actual names of the tunnels. So this particular tunnel, register output 0 select, is specifying which one of the 4 registers inside the bank is going to specify the output for output 0 of the entire bank. Okay, it can be any one of the 4 registers. So that's why in the encoding here, it is specified as XX underscore field because it depends on which variant of this instruction we are talking about. Are we talking about JMP-A? Are we talking about JMP-B, JMP-C, or JMP-D? So this table allows a lot of flexibility when we get to the right slice function, which automatically interprets XX field and go like, oh, we're dealing with not a single opcode, we're dealing with a family of opcodes. And it will go through all the registers, all the variants of the same opcode, and spew out the ROM or the microcode slices for that particular opcode. Is that okay? So one thing you can do is really just to print out the source code of every single one of these instructions and bring it with you. Okay, but don't forget microcode because that's also useful. But that's still not the optimal solution because it means you have to kind of count and then correspond, and it would be much better if the whole thing looks like a spreadsheet, right? You got, I would do it in a way where the 18 bit fields are the rows, and then the instructions are the columns. I guess you can flip it either way because I think we have about 18 instructions too. So it's not, the table is going to be look more or less like a square. So it doesn't really matter which ones are the rows and which ones are the columns. But I would use a table. But this is not giving you a table. So what do you do to turn it into a table?
Use spreadsheet.
Huh? Okay, so you want to do the minimal work, right? Because I want to do the minimal work all the time. So how do you do the minimal work and get this to work? I got the basic stuff here already. All right, so now you have to remember what you learned in your C class, in cisp310. Okay, you basically look at this code here, okay, and go like, can I keep read ROM? Can I keep read write slides, but change the implementation? The answer is, yeah, sure, why not? Okay, so you go to this particular file, this is microcode.c, and read ROM is implemented here, and it's kind of like, and it causes parse ROM and a whole bunch of stuff. But in your case, you don't need it to do all the fancy stuff like this. So in your case, read ROM can just read everything from standard in and echo everything back to standard out. Okay, doesn't matter what it is. Okay, if you read a byte, spew out the same byte. If you read another byte, you spew out the same byte. Okay, and then so that's the entire read ROM. When you look into write slides, okay, write slides is kind of complicated. It has got a lot of stuff here. This is also where the XXYY stuff is parsed. Okay, so you don't need write slides to be this complicated. Your write slides is literally just going through the slides, which is a parameter, which is here. So your code can just go through the entire slides and print out each value tab separated from the next one. Okay, that's all you need to do. Now you might want to treat XX field and YY field a little bit differently, and just write the character X or the character Y in place of the negative number, because otherwise it just looks kind of confusing. Okay, but that's what you can do. The other thing that the existing program doesn't do is write slides is only interested in the opcode, but it doesn't spew out the mnemonics. Because guess what? The ROM doesn't need to know the mnemonics. The ROM just needs to know, oh, this instruction or this slice goes here in the ROM, and that's all it needs. But when you're dealing with your table, you want to spew out the mnemonics too. So what you need to do is to change the prototype of write slice to include a string as the first parameter, so that way you can pass JMP in this case as the actual mnemonic. So when you have the table, each row has a mnemonic corresponding to it. So it makes it easier to look up things. Is that okay? And yes, you do have, I give you the license to change all this code. It's open source. As long as you don't claim that, yep, I wrote this whole thing. Is that okay?
You want us to print the first page you have on the Sambo manual?
Just copy and paste it and say this is open source and it's contagious. Yep. Okay, so, but that's the idea, okay? This is not something that you have to do, but this is something for those of you who feel comfortable with coding and go like, oh, I just want to generate, a tab separated value spreadsheet so I can import it into Microsoft Excel, LibreOffice, or Google Sheets, and then you have your nice, little printout. That's something that you might want to consider doing, okay? You can always do it by hand. Okay, if you don't mind and do it by hand, that's okay too. So I will show you what it means by doing this by hand. Okay. So doing this by hand means that you have to go to a spreadsheet, and then you at least will need all of these as column or row names, and then you have to copy these into the cells. Okay. Okay, I'll show you exactly what I mean by that. It's going to take a little bit of time because this is. So I'll show you the first few steps, and then you guys can deal with the rest. Okay, so the first one is mnemonics, M-N, mnemonic. Okay, there we go. So the mnemonic is the first one, and then we start to copy this stuff here. So this is microcode pointer reset, microcode pointer select. PC enable. Okay, I'm just going to do the first three. Okay. All right. So now you have to copy the mnemonics. So the instruction that we're dealing with here is jump. Okay. So you basically say the mnemonic of this one is JMP, and then you copy all the rest. Okay. 0 goes here, 1 goes here, and 1 goes here. 7 goes here. 7 is PC mux mux. Like so. And when you're done with the jump instruction, there are 18 columns that you have to fill up. Then you move on to the next one. Okay, I would group instructions by functionality. So the next one that I want to use is probably JMPI. Okay, you look at JMPI, do the same thing. So we have JMPI. In this case, we got 0, 1, oops, 0, 1, 1, 7, 1, and so on. Okay, they have the same beginning, but the endings are different. Okay, so you basically just make a table like this. You can do it by hand, you can do it by the program, but this will give you a very easy way to visualize and say, okay, who makes use of RAM? Look at the column. Okay, if there's a 1 in RAM cell, that instruction, the corresponding instruction, makes use of RAM. Which one changes the program counter? Look through the whole thing. Whichever one has PCEN being a 1 changes the program counter. Is that okay? So this will be helpful because I'm expecting you guys to understand how the processor works, how microcode works. In this case, you may understand the whole thing, given enough time, but how to get to each instruction really quickly, that's what this table is for. Are there any questions about this part? Just one more tip. In a real spreadsheet, you can rotate these things. So you can basically select the top row, and you go to Format. You can go to Align, and this is. Google Sheets can do only so much, but when you use Excel or when you use LibreOffice, you can rotate those texts so that they are actually like 90 degree. That makes it easier to fit all the things that you need to fit.
Text rotation. There's a text rotation option right there.
It has
text rotation, 3 lower.
text rotation.
Under Align.
Align, merge, text,
Lower.
merge, right.
Oh, right there. Okay. So I can tilt up, tilt down, stack vertically. Oh, cool.
I think stack vertically is the one.
That may not be easy to read.
Stack vertically.
Oh, like that.
that to me that's harder to read. Maybe to some people it's okay, but to me that's actually harder. But you can play with this and find out which way works best for you. So when you go under Align, text wrapping or rotation, I would just tilt it up a few times, maybe. Can you tilt up one more time? Can I stack tilting?
The tilt up is the
Oh, okay.
can
But
do
we
it,
can
yeah.
change the degree.
90 degrees.
90 degree. There we go.
That's what you're
Okay.
looking for.
So there you go. You can do the same thing in Google Sheets. So you can do the whole thing in Google Sheets. So the idea is you can either hand copy everything, which is not recommended. I hate boring chore. So if modifying the source code takes even slightly more time, I'll do it that way because it's just a whole lot more fun. But that's just me. You know, you guys choose whatever you want to do. Okay, so you can make it smaller and fit everything here. So that's one table that you might want to make. Okay, by hand or by program, you'll just do this table. So are there any questions about where to find out what instruction makes use of what microcode?
It's a two-dimensional array, so what's the second dimension for?
The second dimension is, so you have the next instruction here, so you could say JZI, for instance, JZ. So then you look up the JZ instruction. Oops. And then you copy these numbers. 0, 1.
Yeah, I meant the ones under that though.
Under what?
Because you have.
You mean here?
No. Back on the other one. There's two sets.
Oh, you mean this slice?
That, yeah.
Oh, the second slice is always the same because the second slice only has a 1 for the first bit field to reset the microcode pointer, so that we go from whatever instruction we are dealing with back to location 0. Because location 0, which is also called no op, is really the fetch part of every single opcode. So that's why we have a 1 for the second one. So the second one you don't want to copy because it's all the same. Yep. It's just the first slice that matters. Okay. So is that okay so far? Does everybody kind of understand what you need to understand to kind of answer the questions? So that's the first half. So the first half has to do with the processor architecture, has to do with microcode, and you might see questions where, okay, this is the new instruction I want to implement. Why is it not possible? Or is it possible? Okay? And if it is not possible, what changes do we need to make to the processor to make it possible? So that means you really need to understand the processor architecture well in order to answer those questions. Okay? You also might want to bring several printouts of this, because one single printout, you may find out that, okay, I used one for one question already, and I need a separate sheet for the second question or something like that. So if you make multiple copies and bring just multiple copies of that, you can just say, okay, this is for question 1, this is for question 2, just in case you need multiple of these. Is that okay? All right. Sort of. Yep.
How many questions?
I would say about 5-ish. Okay, so that's the first type of question. First type of question has to do with the architecture itself. We are looking into each instruction and say, okay, how is each instruction implemented? The second part is going to be on a macro scale, which means I give you the C code, you give me the assembly code. You have done that several times with your homework already. Okay. So what is next is going to be decompiling. Okay, I think we talked about decompiling a few times. Yes. Okay. So what you want to do with decompiling is to look into some existing code that we already have. And so you go to processor, shared, not necessarily processor, but there are a few examples that we have done already. So you want to kind of strip all the comments and see if you can reverse it. But we also have final exam here. And you want to look into this final exam because it has got some of those questions. So in the final exam last semester, they're all questions like that. Okay. So question number 1 is giving you the C code, and you have to implement the C code in assembly code. Okay. It's not much more complicated compared to division. Okay. This one is really just about the same, I would say. Okay, so are there any questions about this one? If not, I would skip this question because it's not really one of the more difficult questions. It's kind of like a warm-up question. The second question is to decompile. So this one may be a good one to kind of look into. So this is the one where I give you the code, and then you have to tell me what it does. Okay, you have to reverse this back into C code. And according to this, okay, be sure to use structure code. In other words, I don't want to see conditional, if blah 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 go to a label. Okay, I want to see actual structure code where there's if then else, while, do while, that sort of thing. And I want you to infer as much type information as possible. Okay, is this parameter an integer? Is it signed? Is it unsigned? Is it a pointer to an integer? Tell me all of that stuff. As much as you can find out, tell me about the types of those things. Tell me about the type of the return values and also the parameters or local variables. Okay, so you have to identify all of those things. So do we have any questions at this point? Yep.
For the else statement, do you use a different conditional jump, and then when it ends with the if statement, you use an unconditional jump?
Right. So that information, okay, so the basics of all of that stuff is discussed in assembly language programming, and I think it is in compiling C control structures. There we go. So this is what you want to read to kind of understand the template of assembly code. So a simple conditional statement will translate to something like this. So you have a block of code here, you have another block of code here, but after the first block of code, you have an unconditional branch to the end here. Okay? If you have no else, then it's a little bit simpler. You basically have a way to go to a end label, which is after the entire block. Okay? When you have a while loop, okay, you start from here, and in the while loop, if you're only given the assembly code, then you try to identify a structure like this, where there's a label right after a unconditional branch back to an earlier label, and then there's a conditional branch to go to the label that's right after the unconditional branch. So that's what you're looking for. Okay, the branching is a big clue of the control structure, and how you use the stack pointer. Register D is a good clue to find out what is on the stack. How many parameters do we have? Okay, is that okay so far with this? Okay. All right. So this is not the example that I used in the previous class. So I'm gonna get out of this one because I got one that is better, and I'll try to find it here. I think I may not have shared that, so I'm gonna go to the final exam of the previous semester, and we'll share this one up to that. Okay, so we'll make a copy of this and move this to the share folder. So we'll move this one to, oops, too far. 10 shared final exam. There we go. Okay. So now when we go back to the share folder, under final answers, there's a new it's called copy of a copy, but it really is not. I think this one is correct. Yep, okay, this is the right one. So this one is not exactly the same as the one that we saw earlier, even though it's called a copy of the same thing. It really is not, because I changed after I made the copy. So, and this is the program that I want you to kind of try to disassemble. The other one you can try to, but that one is really tedious because that's before I implemented the increment and the decrement instruction. This one is after. So it's actually a lot cleaner. Okay. So we'll take a look at this code and figure out what we can do with this. The way that I'm going to do this is I am going to turn this into a PDF first, and then so I can use a document, use my tablet to explain how that is done. So we'll go ahead and do a print. Nope, that's not what I want to do. Cancel. There we go. Because I just need to export because I'm already on Google Documents. So an export would do download. I thought there's an export as PDF. Yeah, I can download and then re-upload it, right? That seems just kind of extra steps to what I want to do. Okay, save. And we'll save this as 2017 spring final exam. And then go back to here and then re-upload it. Cool. Oh, no. And this file is, you can access it to because it's under the share folder. So now I can go back to my tablet and then import that exam from my drive. Shared. And we're looking at final answers. And this is this one. Select. And create and open. There we go. Okay. Cool. Okay, so we just need to go to that question, which is the second question. Okay, so with this question, what the best way to do it is to kind of write on the side, or if you want to bring extra sheets of paper, that's fine too. Okay, so with this one, where do we get started? You always go with the easiest stuff first, okay? Because in case you run out of time, okay, you get the easiest stuff done, you get partial credit for that. If you start with the hardest things and you can't even get close to the point where I can give you partial credit, then you're kind of not getting any points for all the effort. So always start with the easiest stuff first. Easiest stuff is to go into a subroutine and you say, oh, I think I can identify the end of a subroutine. So let's turn on zoom again. Okay. 2-finger slide, there we go. So we can identify a few things for sure. Okay, these three together is what?
Return.
It's a return. Okay. Now when we say return, we have to be kind of more specific. This is returning to the caller. Okay, it's transferring control back to the caller. Okay. Okay. So this is so we'll just say this is return to caller. Okay, and I'm gonna pick a fine pencil here. What about that statement right before that? Okay, subtract AB. What do you think that's doing?
A equals A minus B.
But specifically, what is the significance of register A when you're in a subroutine?
A is the return value.
It's the return value. Okay, so we are specifying something as the return value. We don't quite know exactly what it is, but we know it has a return value. Okay. So now you start from the beginning. Okay, the one thing that you're guaranteed is at the beginning of any subroutine is register D, or the stack pointer, okay, is always pointing to the return address. This is guaranteed. It is the agreement between the caller and the callee. Okay, if there are parameters, they're on top. In fact, if there's a parameter 1, it's here. If there's a parameter 2, it's here. If there's a parameter 3, it's going to be on top. Okay, so that is also part of the agreement between the caller and the callee. So now what you want to do, in the test, is you want to kind of comment on all of these lines here, and you want to say, okay, we just make a copy of register D to register B, so B would point to the same thing, which means B points to the return address. We increment B. There wouldn't be any reason to increment if we are looking for something on top of the return address. So now B points to param 1. Okay, now we have a dereference. Okay, LDAB is not copying A to B, it is copying what B points to A. Okay, so effectively what we are doing is saying A is now whatever B points to, which is the same as param 1, not the address of, but the value of the parameter. We increment b again, so b now points to param 2. And we dereference b and then put the result back into b. So that means b is now param 2. Is that okay? So when we do the subtraction, the return value is actually param 1 minus param 2. Is that okay? Okay, so according to this, we are doing subtraction. I can probably safely claim that param 1 and param 2 are integers of some kind. Is it signed? I don't know. Is it unsigned? I don't know, because the only way you can tell whether something is signed or unsigned is when you compare. After you compare, if you use a JL, it is signed. If you use a JC, it is unsigned. I don't see those instructions here. I do not have any clue of whether it is signed or unsigned. So in the if there's a lack of information like that, you can just say, okay, it's some kind of integer. Signed or unsigned, we get full credit. Okay? So in this case, so basically what we'll end up have here is the return value has the same type as the parameters. Okay? So you can just say int. You don't even have to say it's 8-bit. Okay? Int is fine. So we have sub1. It's got 2 parameters. Each one is an integer. So we got param1 and int param2. And then inside the subroutine, it has one single return statement, which returns param1 minus param2. And that's it for sub1. So are we still doing okay so far with the analysis of the subroutine itself? So the only thing that is kind of tricky is when you're talking about C, the single return statement has 2 things to do. It specifies the return value and also return control back to the caller with one single statement. But in assembly, they are distinct. Okay, you specify the return value first, then you return to the caller. So you kind of have to remember that those things are separate in assembly, but they combine to the same statement in C. So as it turns out, in this case, main is the interesting one. Okay, so when we get back to main, okay, so this is just initializing the stack pointer. Okay, so that's nothing really interesting here going on. So we are basically just initializing the stack pointer. Okay, no big deal. We are now allocating a byte on stack. Okay, so you might want to keep a picture of what the stack should look like at this point. So we are basically saying, okay, we are decrementing the stack pointer. So the stack pointer is now pointing to a particular location, but we are not storing anything to it, and then we immediately decrement again. So that means this byte has some unknown value. It is not initialized. Okay, it's just something there, and then we start to move on and say, okay, now the stack pointer points to this location. And then we have load B with 4, and then we store. So I'm going to combine these into one thing here. So we have the stack, we have this, and then we have a 4 stored into the location. Okay, and then we decrement again, so that we have question mark, not a bracket anymore for here, and then the bracket moves onto here, but we don't know what is here. So we decrement D. We also decrement B. B had a value of 4, so now it would have a value of 3. So by the time we finish executing this instruction, the stack would have unknown 4, and then the stack pointer points to a byte that has a value of 3. Is that okay? And then we decrement again, okay, which means we have question mark 4, 3, and then the stack pointer points to this location where the content we don't really know exactly what is there. But we decrement B one more time, and then we store B. So now the stack will be like question mark 4, 3, and then we have a 2, and that's where the stack pointer points to. Is that okay? Okay, we are running out of time in the lecture, so I will continue with this over at the lab. Okay, so we will carry on the discussion in the lab session. It will still be recorded. Okay, as long as I don't have any technical difficulties, it will still be recorded. But I think if you guys show up, you know, you can ask questions interactively. That would be beneficial. But if you have something else that you have to do, which should not be scheduled, because that would be a schedule conflict, right? So we'll continue over at the lab. I'm gonna close this first. This is the